Solving absolute value inequalities, part 1. So we're going to solve these by definition. So to solve these by definition, the first thing we have to do is make sure that the absolute value is isolated. And in example 1, we have the absolute value of t, and it's all by itself on one side of the inequality. And now we need to check to make sure that it'll have solutions. And we know that an absolute value is non-negative. That means that the smallest value it can be is 0. So if we check that, just assuming that, say, it's 0, can we think of a number as 0 greater than 2? Well, that doesn't make a lot of sense. But can we think of a non-negative number which is greater than 2? Well, certainly. 3 is greater than 2, 5 is greater than 2. There are lots of them. So this is going to have solutions. Once we've determined that the absolute value inequality is going to have solutions, then we're going to set up our two inequalities. So my first one, I just dropped the absolute value bars, and I have t is greater than 2. My second one, I'm going to take my t, I'm going to flip my inequality, so now it says less than, and then I'm going to change the sign of my number to negative 2. So I have t is greater than 2, and t is less than negative 2. And now what I'm going to do is I'm going to graph these two inequalities. So here's 0, here's negative 2, here's 2. In the first one it says t is greater than 2, so starting at 2, my arrow should go to the right. And since it's strictly greater than, I use a parenthesis. For my second one, it says t is less than negative 2. So since it's less, it goes to the left. And once again, since it's strictly less, I use a parenthesis. Now that I have my graph, I can see that my first interval goes from negative infinity up to, but not including, negative 2. And then I've got this gap here, and that's going to be my union, so that I can bridge that gap. And then I continue on from positive 2 to positive infinity. And that is my solution set in interval notation. Example number 2 is similar. My absolute value is isolated, and I think to myself, can I think of a non-negative number which is less than 5? Well, yes, I can. 4, 2, negative 10, any of those would be less than 5. So I set up my two inequalities. X is less than or equal to 5. And then the second one, x, flip my inequality, greater than or equal to, and change the sign of my number, negative 5. And then once again I will graph these two. So I have negative 5, and I have 5. The first one says x is less than or equal to 5. So from 5, I would need to move in towards 0. And since it's less than or equal to, I want to include 5. So I would use a bracket. For the second one, x is greater than or equal to negative 5. So from negative 5, once again, I move towards 0. So these two intervals are moving toward one another. And once again, I would use a bracket. Whenever we have the two inequalities moving toward one another on the graph, we're only going to get a single interval. And we can see this single interval is from negative 5 to 5. And we use the two brackets to say that we're including negative 5 and 5 in our solution set. For number 3, we have the absolute value of x plus 5 is greater than or equal to negative 4. Now the key to remember is that when we have these inclusive inequalities, greater than or equal or less than or equal, only one of those has to be true in order to make this whole inequality true. So if the absolute value is greater but not equal, that's okay. So we know that the absolute value is non-negative. Well, any non-negative number is going to be greater than negative 4. because the smallest the absolute value can be is 0. So 0 is certainly greater than -4, and so are all the positive numbers. So in this case, we really don't need to write anything out other than the fact that we know that the solution will be all real numbers. If we want to state all real numbers in interval notation, then we just say it goes from -infinity to positive infinity. In example number 4, we have the absolute value of y minus 7 is less than -9. Now once again, we have to remember that this absolute value is non-negative, which means the smallest it can ever be is 0. 0 is not less than -9, and no positive number is less than a negative number. So this one has no solution. In our last example, number 5, we have a non-negative number which is less than or equal to 0. Well, we've already stated that a non-negative number can't be less than 0 because the smallest that this absolute value will ever take on is the value of 0. So we know that the first condition cannot be met. The absolute value of x plus 2 cannot be less than 0. But we've got two conditions. We've got the condition of equality as well. So this could be true in the one case where it's actually equal to 0, and that's the equation that we want to set up. X plus 2 is equal to 0. That's the only thing that's going to make this inequality true. So then we solve this, subtract 2 from both sides, and we've got the single solution x is equal to -2. Now, if we wanted to use set notation, we're not going to use an interval because this is a single value. The only thing we could do is use our curly brackets, which we use for finite sets, and just put the single value of -2 in the curly brackets. That's the only value that's going to make this inequality true, and we can prove it. If I write the absolute value of -2 plus 2, I'm replacing the x with the one single value -2 that I said would make this true. We're going to test whether that's less than or equal to 0. -2 plus 2 is 0, so that gives me the absolute value of 0 is less than or equal to 0. And the absolute value of 0 is 0, so we get 0 is less than or equal to 0. Well, it's certainly not less than 0, but it is equal to 0, and so it meets that condition, and therefore this is true. 0 is equal to 0.